Have you ever looked at an earthquake recording? It's just this messy, chaotic scribble on a screen. But somehow, software can take that jumble and perfectly pick out the simple, clean vibrations that it's made of. So, how does it turn that complete chaos into a clear recipe of ingredients? Well, that's exactly the puzzle we're going to solve today. So, really, how does this work? I mean, we're handing a computer this one incredibly complex signal, basically a language it doesn't speak, and its job is to translate it. It has to come back and say, okay, inside that giant mess, I found this much of a slow wobble, a whole lot of a faster one, and maybe just a tiny hint of a really fast vibration. Believe me, it's not magic, but it is an incredibly powerful tool. To really get our heads around this, let's think about it in two totally opposite ways. First, there's the way you might learn about it in school, which is kind of like building with Legos. You start with a bunch of simple, known pieces, and you snap them together. But what this software actually does is the complete reverse. It takes the finished, complicated spaceship and works backwards to figure out exactly which individual bricks were used to build it. So let's take a quick peek at that textbook method. Because once you understand this super simple approach, it makes the power of the real method, well, that much more impressive. With this textbook approach, it's like we have all the cheat codes up front. We just say, hey, let's take this slow wave and this fast wave and just add them up. It's a great way to see how waves can combine, for sure, but it's not really useful for analysis because in the real world, you never, ever start with the answer key. You always start with a jumbled up result. Okay, so if you don't start with the simple waves, how in the world do you find them? Well, you need a deconstruction tool. And that brings us to the real method and the star of our show today. Meet the Fast Fourier Transform, or FFT for short. This is the powerhouse algorithm, the secret sauce that lives inside all kinds of analysis software. Its entire job is to perform this incredible transformation, to take a signal that's measured over time and give us a brand new perspective on it as a simple list of frequencies. It's the ultimate deconstruction tool. So, how does software actually put this amazing tool to work? Well, it's the heart and soul of a really slick 5-step workflow that takes raw data from pure chaos to crystal clarity. Here's the whole journey laid out for us. The data comes in raw, it gets completely deconstructed by the FFT, then we get to analyze and even change those individual parts, and then we put it all back together again. Let's follow a signal through each one of these steps. Okay, step 1. Everything starts with data recorded over time. Just picture an earthquake sensor. It's not just spitting out one number, it's recording this constant stream of data points, moment by moment, telling the story of how the ground is moving. This right here is our raw, complex signal. And here it is, step 2. This is where the magic happens. We take that messy time-based signal and feed it straight into the FFT. It crunches the numbers, and what comes out the other side is a completely different way of seeing the exact same information. Instead of a jumbled wave, we get a recipe, a neat, orderly list that tells us exactly how much of each pure frequency was hiding inside our original signal. But here's what makes this so incredibly powerful. The FFT doesn't just tell us that a frequency exists, oh no, it gives us way more detail. For each and every frequency, the output is something called a complex number. Now, I know that sounds a little intimidating, but for what we're doing, just think of it as a special package that holds two absolutely critical pieces of information. So what's in this complex number package? Two things. First is the magnitude. That one's easy. It's just how strong that particular wave is. Think of it as its volume. The second thing is the phase, and this just tells us the wave's starting position. Like when we started recording, was it at the top of its peak, the bottom of a valley, or somewhere in between? So we don't just know what's in the signal, but also how all those little waves are lined up together. And this really nails the key takeaway here. When a piece of analysis software talks about the 1 Hertz component, that's not some vague, fuzzy idea. It is pointing to two very specific, concrete numbers: the exact amplitude and the exact phase of the 1 Hertz sine wave that it found hiding inside that complex signal. Okay, so we've deconstructed our wave into this perfect ingredient list. Now what? Well, this is the part I find absolutely amazing. Now we can actually mess with those ingredients individually. This is where something called a transfer function comes in. It lets us predict how our signal is going to change as it passes through a system, like how earthquake waves get amplified when they travel through soft soil compared to hard rock. And honestly, the math behind it is surprisingly straightforward.
We take our original ingredient list, that's our input, which we call X. We multiply that by H, which is the system's rulebook. You know, how that soft soil is going to change things. And that gives us Y, our final output, which is the brand new signal after it's gone through the system. We've done our analysis, we've modified our recipe of frequencies, so the last step is just to put the puzzle back together. For that, we use an inverse FFT. It does the exact opposite of the original. It takes our new, modified ingredient list and perfectly reconstructs it into a brand new time-based signal. And that is our final output waveform. Now, before we wrap this up, there's one really common point of confusion I want to clear up. The word spectrum gets thrown around a lot, but in this context, it means something very, very specific. So, everything we've talked about today, the whole thing, has been about the Fourier spectrum. That's where you take one signal and find its many ingredients. Now, you shouldn't confuse this with a response spectrum. That is a totally different tool. That's where you take one signal and see how many different buildings would react to it. For what we're doing here, deconstructing a wave, it's all about the Fourier spectrum. Okay, let's bring it all home. We started out by looking at two different ways of thinking about wave analysis. So let's put them side by side just one last time to really lock this concept in. This table really just lays it all out, doesn't it? Check out the starting point. The educational model begins with the simple waves. It already knows the answers. The real process, what Shake actually does, starts with a complex signal. It starts with a question. And the goal is the complete opposite. One is to build, the other is to deconstruct. It truly is the difference between starting with a box of Lego bricks and starting with a finished spaceship, trying to figure out how it was made. So in the end, the FFT is this incredible lens that lets us see the hidden simplicity buried inside all the chaos. And it's used everywhere, from cleaning up audio recordings to analyzing brainwaves in an MRI. Which really makes you wonder, doesn't it? What if we pointed this lens at something like the stock market, or weather patterns, or even social media trends? What simple driving frequencies might we find hiding there, in plain sight?